Now, coming to the non-existence of the helium molecule. Last class we have seen it, the existence of the hydrogen molecule, how hydrogen molecule is being formed by valence bond theory. Now we'll understand the non-existence of the helium molecule. Why He2 molecule does not exist? Why He2 molecule? Now see here. That is, we have seen a graph. We'll understand it graphically. That is much more better. You will see it. So here we have taken the potential energy, and here we have taken the internuclear distance. Internuclear distance. So what you find is that when the helium atom is at infinite distance from one another, so it has no attractive forces or repulsive forces. Two helium atoms, when they are far apart from one another, considered to be at infinite distance. So it has got neither any force of attraction nor any force of repulsion. Fine. That is, now in case of hydrogen we have seen it, that when the two hydrogen atoms they come closer to each other, what happens is that the attractive forces increases and the repulsive forces decreases. So the graph you have seen it, that is when the atom is approaching, the energy is decreasing. Alright, energy is decreasing. You have seen the graph, it is because when the attractive force is increasing, energy is released. Alright, energy is released, exothermic, and hence the stability increases. After that we have seen the graph is again rising. Why? Because we are having an internuclear distance beyond which it's not possible. Why? Because the nucleus is going to repel one another. So we are having a particular bond length, we are having a particular internuclear distance, we are also having a particular bond energy, everything we have seen it. So here also same thing is going to happen. Here also, but it is be different. So when the internuclear distance will decrease, when the two helium atoms are far apart from one another, when the two helium atoms and they are approaching each other, what you will find? You will find that the graph is increasing in this way. Alright, see here what happens, energy is increasing because as the what you can say, the atoms will come closer and closer to each other. As the atoms will come closer and closer to each other, see the internuclear distance is going to decrease, not in this way, it is decreasing, the atoms is approaching each other. So energy is increasing. Why? Because they are repelling one another. There is no force of attraction at all, they are going to repel one another. Why? Because the two helium atoms, the outermost shell is fully filled. Why they will undergo bond formation? They are quite stable. For that particular purpose you can see in this particular graph, when the two helium atoms approach each other, their internuclear distance is decreasing, but the energy is increasing. In case of hydrogen atoms, what it was? When the internuclear distance was decreasing, energy was decreasing. Why? Because attractive forces was more than the repulsive forces. Here, as the helium atoms approach each other, the repulsive forces is more. There is no question of any attractive forces here. And hence, what you find is that energy increases. Due to which, what you will find is that never two helium atoms will combine and will form a molecule. Because they are quite stable in nature. Rather, if you try to bring them closer to each other, repulsive forces is more and they will never form a molecule. And the energy will be more and more. You have to, definitely you have to provide energy to it to bring them closer, because they will not come closer by itself. You have to give energy to it. To give energy means energy is increasing. Energy is endothermic. Alright, so you can see in the graph that is, it is increasing in this way. Now we will understand in one more way, we will understand it. Like in hydrogen we have done it, here also we will do the same thing. So we are having, that is nucleus which contains two positive charges, here also two positive charges, and we are having two electrons. That is, let me make it a little bit far apart so that I can draw the lines. Yes, two electrons here and two electrons here, we can say that. Or fine. In this way, we have kept that is two, what you can say, we have taken two helium atom. This is one helium atom, this is another helium atom. These helium atom contains two protons and two electrons, and this helium atom contains two protons and two electrons. As you can see, two protons and two electrons. Fine. So what are the different kind of forces is there? First, let us see the attractive forces. The attractive forces is between, what you can say, I am drawing with a blue line. This is attractive forces between this and this. This is the attractive forces, this is the attractive forces, and this is the attractive forces. So we are having four attractive forces. Got it? 4 attractive forces. Now let us see the repulsive forces. Now this is your repulsive force. I am drawing with the solid lines. This is your repulsive force, another solid line. This is a repulsive force, another solid line. Got it? Now this is another repulsive force, we can say that, and this is another repulsive force, we can say that. So how many repulsive forces? 1, 2, 3, 4, 5. We can say that there are 5 repulsive forces compared to 4 attractive forces. So repulsive forces is more than attractive forces. So the formation of helium molecule is completely, what you can say, we are completely, what should I use the word here? It is ruled out. We can say that it is completely ruled out, because repulsive forces, as you can see, it's more than the attractive forces. Hence helium molecule does not form. He2 molecule for that reason does not exist. Now I hope you understood why He2 molecule does not exist. Now coming to that is your valence bond theory. That is a theory already I have said you, which was given by Hitler in London. Now I am going to start the postulates, which is given by Pauling and Slater. The postulates of the valence bond theory. Now one by one I will come to the postulates and I will explain you. The first postulate is that every atom has a tendency to pair up its unpaired electrons with the oppositely charged, with the oppositely spined electrons of the other atom. Now every atom has got a tendency to pair up its unpaired electrons. Suppose an atom A and atom B is there. Got it? Now it has one unpaired electron and it has also one unpaired electron. So they will have a tendency to pair up. Got it? They will have a tendency to pair up in this way. So every atom has a tendency to pair up its unpaired electrons with oppositely spined electrons of the other atom. Now oppositely means if this is in this way, of course this has to be in this way. Of course when they will come closer together, then they will arrange itself. Don't worry about it, we have read in VSEPR theory. Alright, if you draw this one in this manner as I have drawn it earlier, it's not wrong, not at all wrong. Because when they will come closer to each other, we have read in VSEPR theory, they will arrange itself in such a manner that the force of repulsion among them is minimum. So they will arrange itself, or you can draw in this way also. Alright, to understand it better, you can draw it in this way also. Alright, so both the things I have said you, mind it. So in this way, every atom has a tendency to pair up its unpaired electrons with oppositely spined electrons of the other atom. Fine. Now half-filled atomic orbitals of two atoms having electrons with opposite spin come in proper alignment, which I said you just now to you. They will come in proper alignment. Got it? Suppose we are having this particular, let us say atom is there. So this and this, and we are having another two atoms. Let us say we are having another two atoms. So when they will undergo bond formation, you know what is going to happen here? They will come in proper alignment in this way. They will arrange in this manner. Initially, what you find is that this you can see all are either clockwise or you can see all are anti-clockwise. But when these two atoms will approach this unpaired electrons, it will arrange itself, you can see. If this is clockwise, then it becomes anti-clockwise. If this is clockwise, then it becomes anti-clockwise. They will arrange themselves. They will come in proper alignment and proceed towards one another to overlap. They will proceed towards one another to overlap. Alright, when the two atoms, the half-filled orbitals, it is there, the partial filled orbitals, it is there, the electrons are there, when they approach each other, they will come in proper alignment and they will proceed towards one another to overlap. Overlapping of atomic orbitals of two atoms gives rise to a molecular orbital or covalent bond. Yes. So when these atomic orbitals, partially filled atomic orbitals or half-filled atomic orbitals, this is half-filled atomic orbitals, when they overlap, this is, remember it, atomic orbital, when they overlap, they form what? A stable compound, a stable bond. What is that known as? It is known as a covalent bond. And what is the orbital known as? It is known as a molecular orbital. We can say definitely. Atoms combine to form what? Molecule. These two atoms they will combine and form what? Molecule. These two are atomic orbitals. Alright, they will come in proper alignment. They will proceed towards one another and they will overlap. They will overlap to form what? A covalent bond. And the molecule is known as what? And a molecule is formed, which is otherwise known as what? Molecular orbital. We can say that. From atomic orbital, it gives rises to molecular orbital. Definitely atomic orbital is unstable in nature. Molecular orbital is much more stable in nature. Because when they approach each other, when they come closer to each other, attractive forces takes place, energy is released, and as a result, the bond is stable. The compound is stable. The molecule is stable. We can say that. Okay. Now, greater the overlapping of atomic orbitals, the stronger is the bond formed. greater the overlapping of atomic orbitals, stronger is the bond formed. And complete overlapping is not possible due to internuclear repulsion. Now, based upon this, I will tell you two things here. So, greater the overlapping. Now, overlapping can be of two types. What is that? One is your head-on overlapping and another is your lateral or sidewise overlapping. Listen carefully, this one. This is very important. One is your head-on overlapping, another is your lateral overlapping or sidewise overlapping. Now, head-on overlapping means, I mean to say, this is your head-on overlapping. This one, see here. This is your head-on overlapping. Head-on. This is an atomic orbital, this is another atomic orbital. When they come, this is called head-on overlapping. But when they overlap in this manner, sidewise, this is called sidewise overlapping, this particular one. Or I can take this to pen and I can show you. This is head-on overlapping. You can see it here, head-on. But when they overlap in this manner, this is called sidewise overlapping or lateral overlapping. Now, head-on overlapping, this one. Now, complete overlapping is not possible. Completely, it is not possible. In this way, it is not possible. Completely. Alright, in this way, it is not possible. Alright, it can overlap to a greater extent. Maximum, the overlapping is possible. But this is not possible. Because why? This particular atom, let us say, is having a nucleus. And this atom is also having a nucleus. When they approach each other, there will be an internuclear repulsion. So, one atom cannot completely overlap upon one another. Because this atom is having a nucleus, this atom also have a nucleus. When they overlap, when they come, overlapping is taking place. Maximum overlapping is going to take place. Complete overlapping is not going to take place. Because this nucleus and this nucleus is going to repel one another. Due to internuclear repulsion, complete overlapping is not possible. And remember it, more is the overlapping, greater is the overlapping, stronger is the bond. Greater is the overlapping, stronger is the bond. That does not mean, again I repeat, complete overlapping is going to take place. Due to internuclear repulsion, complete overlapping is not possible. But greater is the overlapping, stronger is the bond. So this sort of overlapping, head-on overlapping is known as sigma bond, sigma. And sidewise overlapping is known as pi bond. Or lateral overlapping, sidewise or lateral, both are same, is known as pi bond, pi. We can say that. So hence, so when, what you can say, sigma bond is formed, this type of bond is formed by the, what you can say, head-on overlapping of half-filled atomic orbitals along the internuclear axis. Alright, along the internuclear axis. And the pi bond is formed, this sort of overlapping is being formed with sidewise overlapping of half-filled atomic orbitals in the direction perpendicular to the internuclear axis. That is, overlapping is going to take place above and below the internuclear axis. Perpendicular to the internuclear axis, that is above and below. I will show you now. Got it? So in this way, we have got two types of overlapping. One is sigma bond, another is the pi bond. Very, very important. Listen children carefully. So, what is that? Here, you can say this is an S subshell. This is an S subshell, which is having a nucleus. This is another S subshell. It can be any S, 1S, 2S, 3S, 4S, 5S, anything. So this is S subshell, which is spherical. They come closer, and what it forms? It forms overlapping. This is called head-on overlapping. See, this particular one is head-on overlapping, and this bond is known as, what is this bond called? Sigma bond. This is sigma bond. Got it? It's known as. Now this is not going to overlap completely upon this, because you can see the nucleus is there, and they will repel one another. So the greater overlapping, maximum overlapping is going to take place. So this is SS overlapping, which gives rise to sigma bond. We can say that. Head-on, remember it. It is head-on. You can see that, because spherical means we don't have any side. Okay, understand it. Now this is S subshell. Now this is another P subshell. Now generally, what you find is that PZ, we consider this as a PZ, this particular, generally we consider it. Clear? So otherwise, as I said earlier also, we have nothing to do with the mathematical coordinates axis we are having in maths. That x-axis will be horizontal, y-axis will be perpendicular, and z-axis will be mutually perpendicular to x and y. No. Here any axis can be x, y and z. We have nothing to do with the coordinate axis of maths. For that reason I said generally this is the z-axis, we take it. PZ, we can say that. Alright, this is a P subshell, no? So PZ, we are having two lobes. Alright, so we consider this as the PZ. Otherwise you will say no, so it is PX. Done. PY. Done. No problem. Alright, yeah. So in this way, this is your PZ subshell, we can say that. Generally we take it. So whatever it is, so here an S and P, when they come closer to each other, what will form? What is going to form here? When S and P they come closer to each other, they will form this sort of overlapping. You can see that. this sort of overlapping. The overlapping is to a greater extent. You can see the overlapping is to a greater extent. This is also is your sigma bond. This is known as sp overlapping. Sp, we can say that, sigma bond. Now this is your p subshell. You can see both the lobes are equal size here. But here you can see when the bonding takes place, one lobe is bigger, another lobe I can make still smaller to show you. Yes, now it is clear to you that one lobe is bigger, another lobe is smaller. Why? Because the attraction is taking place now. Due to attraction, the energy will be concentrated here initially. Then after that, the energy will be released. So what is this? These lobes are made up of what? Energy only. They are made up of energy only. So one side the energy will be more, the other side the energy will be less because energy is released. So hence, how do we show this particular one? When the bonding is taking place, remember that when the bonding is taking place, in one lobe will be bigger, another lobe will be smaller. But if the bonding is not taking place, you can see both the lobes are same size, equal size. But when the bonding is taking place, both the lobes one are not of same size. One is bigger and the other is smaller. The one which is overlapping, that is bigger, and the one which is not overlapping, that is smaller. Why? Because energy is initially concentrated here. Got it? They come closer. Then after that, the energy is released. So energy is more here, energy is less here. Because these lobes, again I am telling you, they are made up of nothing but energy. Alright, clear? Fine. So in this way, this is your p subshell and this is your another p subshell. Alright, this is another p subshell. When they will come closer to each other, this also is pz, you can take that. I have said you already. This also you can take it as pz. So when they will come closer to each other, this sort of overlapping is going to take place. This sort of overlapping is going to take place. You can see. That is, let me make this one smaller. And this one also smaller, so to say. This sort of overlapping is going to take place. So this is known as PP overlapping, we can say that. PP overlapping. This also is what? This also is a sigma bond. So sigma bond is of three types: SS overlapping, SP overlapping and PP overlapping. All these are head-on overlapping, we can say that. And this is your internuclear axis. This is your internuclear axis. This particular axis is called as a internuclear axis. This is known as internuclear. It's an imaginary line. Remember it. It's an imaginary line. It is the internuclear axis. We can say here also the internuclear axis is there. You can say here also it is there. It's not that it is not there. It is there. Definitely it is there. The internuclear axis. So we can say that. Clear? So it is along the internuclear axis and it's a very strong bond, and there are three kinds of overlapping, that is SS, SP and PP. See, this is the difference also, you can say that with sigma and pi bond. So you got the sigma bond. Now I will show you the pi bond formation, how it is being formed. Pi bond. So in case of pi bond, as I said you, the lateral overlapping is going to take place. The lateral overlapping is going to take place in case of pi bond. So this is your one p subshell and this is another p subshell. Generally there was pz, I took it. What it should be here? It can be either px or py. Alright, either it can be px and py. See, this is your internuclear axis. I said that is it, perpendicular to it, or what I said, it can be either above and below. The two lobes will be either above the internuclear axis and below the internuclear axis. Or you can say the internuclear axis is perpendicular to the lobe. Yeah, so it is perpendicular to the lobe, whatever you can say. So let us say this is your px, this is your px. Alright, so when they will overlap, how they will overlap? They will overlap in this manner. Sidewise overlapping is going to take place. See here. Sidewise overlapping is going to take place. So this one. So overlapping is to a smaller extent, lesser extent, you can see. This is your pi bond. Overlapping is to a smaller extent, and here only one kind of overlapping is possible, PP overlapping. There is no question of S overlapping, S subshell overlapping in pi bond. In pi bond, S subshell is not there. Why? Because S subshell is spherical. We don't have any side. What I said you, it is sidewise overlapping or lateral overlapping. S subshell is having any side? A spherical object has any side? No, not at all. So S subshell does not participate in pi bonding overlapping, and pi bond is a weaker bond because you can see the overlapping, but it is divided above and below the internuclear axis, and overlapping is to a smaller extent, lesser extent, whereas in case of sigma bond, the overlapping is to a greater extent, larger extent. Alright, so sigma bond is a strong bond. Alright, and pi bond is a weaker bond, we can say that. Now the shape of what you can say, the molecule is decided by the number of sigma bond, the shape of the molecule, remember it. The shape of the molecule, which you have studied in, which you have read it in VSEPR theory, that is decided by the number of sigma bonds. Shape of the molecule is not decided by the pi bond. Listen carefully. The shape of the molecule is not decided. It does not depend upon the pi bond. It depends upon the sigma bond, because sigma bond is directional. Pi bond is non-directional in nature. We can say that. Now, it can be formed independently between the two atoms. Yes. Now, pi bond, when it is being formed, after sigma bond is formed, then the pi bonding takes place. Whenever the bonding is taking place, listen carefully. Whenever the bonding takes place, alright, like carbon-carbon, you have read it in organic chemistry. What you have read it? First you have done it single bond. Then after that, what you can say is that double bond or triple bond takes place. When the double bond and triple bond takes place, that is your lateral overlapping. Single bond means is your sigma bond. That is your head-on overlapping. So whenever the sigma bond takes place, that is your head-on overlapping. But whenever the lateral overlapping takes place, that is your pi bond. So first sigma bond formation is going to take place. It is independent. First sigma bond. Whenever the bond formation takes place, first is sigma bond. Single bond means sigma bond. Alright. If double bond will be there, 1 sigma, 1 pi. If triple bond will be there, 1 sigma and 2 pi bonds will be there. So first sigma bond, listen carefully, first sigma bond. Then after that, if there is any what you can say electron left for the bond formation, then it will give rise to a multiple bond, and which will be your pi bond. So first sigma bond, then pi bond. So pi bond is not independent. Pi bonds can be formed only when sigma bond has already been formed between the two atoms. Alright, clear? Now there is free rotation of atoms around sigma bond. Single bond, free rotation of atoms. You can rotate it very freely in this way. Freely you can rotate it in this way. Alright, but I have shown in geometrical isomerism, if you remember it, that is two bonds was there. One is sigma and another is pi. There was restricted rotation. Why? Because sigma bond is bigger and the pi bond is, sigma bond is smaller and the pi bond is bigger. Sigma bond is smaller and the pi bond is bigger. Now both the bonds are of not of, both the bond length are of not of same, but you can say size. One is smaller, another is bigger. See, if you try to rotate the pi bond, it is going to break. It is going to break because sidewise, na? If you try to rotate means it is going to break. The bond is going to break. Alright, so there is no free rotation around pi bond, but there is free rotation around sigma bonds, because sigma bond is single bond, free rotation. As you can see, I am rotating now. It is single bond. But in pi bond, one bond is bigger, another bond is smaller. So definitely the smaller one will restrict the bigger one to rotate. Definitely, you have seen it in geometrical isomerism. I have said it. Alright, there we are having two bonds, one sigma, another is pi, cis and trans. In geometrical isomerism, we have seen it. Alright, for that reason only cis and trans is formed due to the restricted rotation. I have told you there. Due to the restricted rotation only sigma, what you can say, the cis and trans is formed. For that reason, in geometrical isomerism we have studied that single bond has got no geometrical isomerism. Alright, single bond has got free rotation. So no geometrical isomerism is seen in single bond. Triple bond, no geometrical isomerism, because triple bond means it is linear in nature. Linear, bond angle is 180 degree. Only in case of double bond. So the conditions for geometrical isomerism means there should be a carbon-carbon double bond, or carbon-nitrogen double bond, or nitrogen-nitrogen double bond. See, so many things I am saying you to explain you all these things. So already I have said that one lobe in case of pi bond will be smaller, another lobe will be bigger during bond formation or after bond formation. Before bond formation, both the lobes are of same size. But in sigma bond there is no such, because we don't have any lobes in case of sigma bond. We are having a spherical shaped orbital, we can say that. Now, so that is in case of sigma bond, the overlapping takes place symmetrically. It is symmetrical, the overlapping, we can say that. But overlapping of atomic orbitals takes place above and below the internuclear axis, as you can see it. Alright, in case of pi bond, we can say that. So now next is when S subshell participate in bond formation, it gives rise to always sigma bond. S subshell, because I told you already that S subshell is spherical, it has got no sides. So whenever S subshell participate in bond formation, it gives rise to sigma bond. Alright, but when P subshell is there only, it may be sigma or it may be pi bond. If it is head-on overlapping, sigma. If it is lateral overlapping, it is pi bond. Alright, so in this way, it is stronger bond, sigma bond, and pi bond is a weaker bond. I already said you. Alright, sigma bond is SS, SP and PP. Pi bond is only of one time, that is PP. We can say that. Clear? So this is about your sigma bond and pi bond, so to say. Thank you.